Well, hello everyone, and thank you for coming to today's seminar, and thank you, Mathieu, for the introduction. This seminar is going to be on some work done in collaboration with Josme Lopez, Sanki Lee, Dongmin Kim, and Greg Foltz here at PhD, as well as Andrew Mercer at Mississippi State University and Karthik Balguru at PNNL. This research is on the seasonality of interbasin SST contributions to Atlantic tropical cyclone activity, which comprises the first part of my NGI postdoctoral research here at AOML. So a manuscript on this is currently in preparation, so please, I welcome any suggestions or comments that you all might have. So with that, we get to it. So to begin, we have a figure here, figure A at top right, which is a time series of accumulated cyclone energy, which is just the squared maximum wind velocity that's summed every 6 hours of the lifetime of a tropical storm with winds greater than 34 knots. That's effectively a measure of the number, the strength, and duration of storms that have been aggregated throughout a hurricane season, which runs through June to November, or JJASON. Now, the time period here in this time series is from 1950 to 2020, and this is a time domain going to use throughout this seminar, which includes the more reliable tropical cyclone data obtained after reconnaissance flights began. Now, the 5 most active hurricane seasons as measured by ACE are given by the red bars, with the 5 least active years shown in blue. So for example, the above average years of ACE of 2017, 2005, 2004, 1995, they all have ACE values over 200. Now, I don't want to focus explicitly on the recent above normal period or a multi-decadal signal here, but instead I just call your attention to these years in order to reference them in the future. Now, figure B shows the same ACE values, only standardized. So the ACE anomalies for each year or for each hurricane season are computed and then normalized, where the 5 most active years are given by the solid vertical lines here, where the 5 least active years are shown by these dotted lines. So we will be returning often to this type of standardized ACE time series. Now, if we divide the hurricane season into early, which I'll define as June, July, August, or JJA, and late, or September, October, November, SON, divide it into these 2 seasonal components, and again plot ACE from 1950 to 2020, separating ACE or partitioning it into those JJA and SON periods. You get the figure here at top right, showing in orange the JJA standardized ACE values, and in purple the SON standardized ACE values. Again, with the 5 most active hurricane seasons, with the solid vertical lines, and least active with dotted lines. So while interannual variations in the early and late season ACE values are positively correlated, shown here, positive correlation of 0.44, there are some differences in the seasonal distribution of ACE. So below, this figure shows the difference in ACE between JJA and SON during that 71-year period. So positive values indicate that ACE has increased in SON relative to JJA, while negative values indicate that ACE decreased in SON from JJA. So again, those 5 most active hurricane seasons are shown in red, and the least active are in blue. And then we see, even in extremely active hurricane seasons, the proportion of ACE that is weighted towards the early or weighted towards the late hurricane season varies. So for example, that 2005 highly active hurricane season is heavily weighted towards JJA, but then 2017 ACE is heavily weighted towards SON. So this type of seasonal variability in tropical cyclone activities suggests like a need for some seasonally dependent analysis of ACE. Now in the North Atlantic, tropical cyclone genesis and development typically occurs in the Atlantic main development region, and that's typically defined in the tropical North Atlantic and extreme Eastern Caribbean. Now within the MDR, vertical wind shear and convective instability are the dominant local environmental factors that are going to influence tropical cyclone activity. Now, interannual variability throughout the tropics in general has a strong influence on environmental conditions within the Atlantic MDR. Now, for instance, INSO is well known to influence Atlantic TC activity through remote atmospheric teleconnections. So warm SST anomalies in the tropical Eastern Pacific associated with El Nino will typically inhibit Atlantic TC development due to increased Atlantic vertical wind shear, while conversely, cooler tropical Eastern Pacific SST anomalies associated with La Nina will correlate to weaker Atlantic vertical wind shear and a more favorable Atlantic hurricane season. But it's been established, however, that the relative SST difference between the local or the MDR, the Atlantic MDR, and the remote, or we call the tropical Pacific, that relative SST difference influences the magnitude of vertical wind shear and subsidence in the Atlantic basin, and therefore it modulates TC formation and intensification there. So for example, warm SST anomalies in the tropical Pacific will promote increased tropical Pacific convection, which will warm the tropical troposphere and strengthen the Hadley circulation. This flow will enhance the vertical wind shear over the tropical Atlantic basin, which will then result in a less favorable environment for tropical cyclone activity. Likewise, cooler SST anomalies in the tropical Pacific will lead to decreased tropical Pacific convection, which is then reflected in a weakening of the Hadley circulation, a decrease of vertical wind shear and subsidence over the tropical Atlantic, and a generally more favorable overall environment for hurricanes. So together with the seasonal variability in ACE that we saw previously, this work looks to investigate if the relative difference in remote versus local SST influences, if those influence the remote local SST influence ACE differently in the early versus the late hurricane season. Or put another way, we're curious if the relative local remote SST contributions to tropical cyclone activity exhibit a seasonality. And it appears reasonable to think so. Remotely, INSO exhibits a strong phase locking to the seasonal cycle with minimum SST anomalies in the Eastern Pacific found during boreal summer, and they typically increase to a maximum around November, December. Meanwhile, locally, SST anomalies in the tropical North Atlantic tend to peak in boreal spring, early summer, that coincide with the increase in the Atlantic warm pool amplitude, as well as sort of the maximum of the Atlantic meridional mode variance. And this sort of reaches a crescendo in September. So taken together, these remote the timing of these remote and local influences, it seems likely that the remote influence of ENSO may be weaker in the early season compared to the late season, and that the enhanced local variability in the early season might suggest a greater influence of local sea surface temperature anomalies on early season TC activity when you compare them with remote SST anomalies. So we hypothesize that the early season dependence in the interbasin SST relationship with ACE would be weighted towards the MDR in the boreal spring and summer, or the early season, due to that minimum in ENSO variability, while the growth of SST anomalies in the tropical Pacific associated with an ENSO maximum suggests an enhanced role of the remote SST anomalies in the late season. So before looking into the early and late season specifically, let's first establish the influence of the local and remote SSTs on Atlantic tropical cyclone activity during the full hurricane season. So the figure here is a spatial correlation map showing the relationship between ER SST version 5 SST anomalies and ACE during JJASON. So green values are going to denote a positive correlation, while brown values are going to show a negative correlation, and the stippled regions show where the correlations are statistically significant at the 95% confidence interval. So the tropical Atlantic contains a significantly positive SST anomaly ACE correlation that exceeds 0.5. And this region extends somewhat throughout the Caribbean Sea, but is generally centered in the MDR, which is bounded by this red box here. Meanwhile, the tropical Pacific sees significant negative correlation coefficients, specifically those less than -0.3 in the Niño 3 and the Niño 1 and 2 regions. And we denote the Niño 3 region here in blue. So based on this spatial correlation of SSTs and ACE, we identify the MDR as the local region of TC influence, and local being relative to the Atlantic, and the Niño 3 region as the remote region of Atlantic TC influence. And we choose Niño 3 due to the strong negative correlation with ACE seen here, its high positive correlation with Niño 1 and 2 SST anomalies, as well as its overall high degree of predictive skill for Pacific Basin wide ENSO events. So if we take the SST anomalies from the MDR and Niño 3 regions, we standardize them and compute an area average over those regions, we will get the time series shown here at bottom in figures B and C. And each region's respective correlation coefficient between the SST anomalies and the standardized ACE are given in the red boxes at upper right. And they generally reflect the general, the spatial pattern or spatial coefficients for the regions that were shown in the map previously. So at left, a significant positive correlation between ACE and the MDR SST anomalies is seen, and that's expected given the favorable warm SST anomalies that are generally present in the MDR throughout the hurricane season. And likewise, the negative correlation between ACE and the Niño 3 SST anomalies is consistent with the reasoning that the warm tropical Pacific SST anomalies tend to lead to an increase in convective activity over that region in the Pacific, which then results in an increased MDR, vertical wind shear, and subsidence, which then further limits Atlantic tropical cyclone formation and intensification. Now, if we turn now to the early and late seasons, we will split the hurricane season into the JJA and SON periods and just repeat that correlation analysis that we just saw between ACE and the SST version 5 SST anomalies. So the maps at right show the correlation between the seasonally summed ACE and the seasonally averaged SST anomalies during JJA at top and SON at bottom. So in JJA, the strongest positive correlation between ACE and the SST anomalies is centered in the MDR, which seems to reflect the boreal spring to summer dissipating pattern of the AMM. And note that at top right, we again have the correlation coefficients, this time between ACE and the specific local and remote regions. A statistically significant correlation coefficient of 0.42 is found in JJA between ACE and the area averaged MDR SST anomalies. However, you'll notice that the correlation is absent in the Niño 3 region. There is no significant correlation at all between the SST anomalies in Niño 3 and ACE during JJA. And this signifies a very weak remote SST influence on Atlantic tropical cyclone activity during the early hurricane season. In SON, however, Niño 3 recovers and sees this broad, strong negative correlation emerge. And in the MDR, the strongest region of positive correlation is still in the region, but has shifted west a little to the Southern Caribbean. And this is consistent with a sort of developing Atlantic warm pool pattern. Now, looking at the correlation coefficients again, notably in SON, these correlation coefficients for the MDR and the Niño 3 regions are of similar magnitude, which is suggestive that it suggests that the interbasin SST influences on ACE are weighted fairly evenly between the MDR and Niño 3 regions during SON. So from these maps, there seemed to be a significant difference in the relative contribution between the remote and local basins, excuse me, from early to late season. So we can explore the seasonality of the relative SST influence a bit more by looking at the monthly SST anomaly variance in Niño 3 and in the MDR. So the bar plot at right is going to show the monthly SST version 5 MDR variance in red and the Niño 3 variance in blue. So at the beginning of the hurricane season, the SST anomaly variance of Niño 3 is at a minimum, and that is due largely to neutral INSO conditions. But by boreal autumn and early winter, the Niño 3 variance increases, and that is consistent with the seasonal phase locking of INSO. Now, while overall SST anomalies in the MDR express less overall variance than in Niño 3, MDR variance is increased in the early hurricane season, which is coincident with the variance peak of the AMM, which typically transitions to a minimum through SON. The black curve is simply a ratio of the mean monthly like the MDR versus Nino 3 SST anomaly variance, which just serves to demonstrate that the interbasin SST variance is clearly weighted towards Nino 3. In JJA, the MDR SST anomaly variance is about 30% of Nino 3, but this decreases to about 15% by SON. So combined with the seasonal correlation results, this seasonal SST variance profile suggests that while early season Atlantic tropical cyclone activity is dominated by MDR SST anomalies, only in the late season is Atlantic tropical cyclone activity heavily influenced by ENSO. So to model the seasonal contributions of local and remote SSTs to Atlantic TC activity, we invoke a multiple linear regression model to build what we're going to call an interbasin SST index. So for the 71 years of ERSST version 5 data, the JJA and SON SST anomalies for the MDR and the Nino 3 regions have had their seasonal cycles removed. They've been normalized and then area averaged. And the Nino 3 and MDR SST anomalies that result from that are then linearly regressed to each respective season's standardized ACE. So at right are the interbasin indices for JJA at top and SON at bottom, where the observed ACE is in black for the particular season, and is shown together with the predicted ACE from the Interbasin SST index in red, and that is obtained from each regression model from each respective season. Now you can see there's good agreement between the two indices in both the seasons, and that it includes those 5 most active years with the vertical solid lines and the 5 least active years. There's general agreement between these indices in both seasons. And when you look at the correlation between these two time series in JJA, the observed ACE and interbasin index do share a positive correlation of 0.45, but the relationship is even stronger in SON with a correlation around 0.59. So while this relationship is encouraging, while we're encouraged that the Interbasin SST index is able to sort of model or capture some of the observed tropical cyclone activity, we do need to show that the Interbasin index does a better job of predicting tropical cyclone activity than just using MDR or Nino 3 SST predictors all by themselves. So to do this, we compute a cross-validation of the seasonal interbasin indices using a leave one out method, so that we can test the predictive skill of the model. So linear regression models of the interbasin index, we would call an MDR SST anomaly only index and a Nino 3 SST anomaly only index are computed. There's 3 different regressions computed by withholding 1 year of SST data from each year of the 1950 to 2020 period. And this is repeated for each year, during which the root mean squared error of the predicted index to the observed ACE is calculated and then averaged over the period to give the resulting values that you see in the table. And the red cells here in the table signify the smallest root mean squared error for each season, JJASON and JJASON. So in JJA, the interbasin index has roughly equal skill in predicting TC activity compared to an interbasin index. Well, I shouldn't call it an interbasin index. It's an MDR only index. It has roughly equal skill in predicting TC activity compared to an index that's only made of MDR SSTs. However, an index made of just Nino 3 SSTs fares far worse. But the Interbasin index has better performance in describing ACE outcomes during SON than an index containing either just the MDR, SST anomalies or the Nino 3 SST anomalies. And parenthetically, this is also true for the entire hurricane season for JJASON. So this analysis, this exercise here, just again suggests that the impact of remote Nino 3 SST anomalies on Atlantic tropical cyclone activity are quite minimal in the early season, yet become influential later in the late season. So far, to sort of kind of summarize where we're at, there is we've seen that there's a marked difference in the relative contribution of remote and local sea surface temperature anomalies put towards tropical cyclone activity during the early and late hurricane season. So in JJA, there is no significant Nino 3 SST anomaly and ACE correlation. And this signifies a sort of a weak remote SST influence on ACE during JJA and suggests a more dominant local SST influence during JJA. Now, in SON, the interbasin SST anomaly influence on ACE is weighted pretty evenly between the MDR and Nino 3 domains, which suggests an enhanced INSO role in the influence of remote SST anomalies in late season hurricane activity. The interbasin index that we've constructed reflects this minimal early season Nino 3 impact on ACE, as well as the shared influence of Nino 3 and MDR SST anomalies during the late season. So now having this tool, with the interbasin index sort of available as a predictive model of Atlantic tropical cyclone activity, we'd like to take it a bit further and explore whether it has any skill in forecasting early and late season Atlantic ACE. So to do this, we've used NMME SST hindcasts of 8 different models, which comprise about 93 total ensemble members, which share a common time domain from 1982 to 2009. So these NMME SST hindcasts have been initialized with May initial conditions, which is coincident with the May release of the NOAA CPC Atlantic Hurricane Seasonal Outlook. And they also run to lead times that span the entire hurricane season. So for each ensemble member's standardized MDR and Nino 3 SST anomalies are going to be used as predictors for the JJA and SON interbasin indices, and that will produce a forecast of a seasonal value of ACE for every ensemble member. So these forecasted ACE values will then be divided into terciles to categorize the likelihood of an above, a near, or a below average ACE season. So we do this and then use both deterministic and probabilistic metrics to evaluate the forecast skill of the NMME interbasin indices during the early and late seasons. So figure A shows the anomaly correlation of the 8 NMME models in JJA and SON, which is just representing the correlation between the observed and the forecast forecast ACE. Figure B is showing the saturation root mean square error, where saturation RMSE values that are greater than 1 typically indicate that the forecast system is saturated with error and correspond to a negative anomaly correlation. And finally, figure C is going to is showing the ranked probability skill score, the RPSS, which is just a comparison of the probabilistic forecast to climatology. Here, a value greater than 0 indicates a probabilistic forecast skill that's better than climatology. A value less than 0 indicates a skill worse than climatology, and 1 is a perfect score. So in JJA, all the model skills are generally worse than in SON, except for the CFSV2 model scores. And this is perhaps due to the reduced potential predictability of Nino 3 and Atlantic MDR SSTs that occur during JJA relative to SON. Anomaly correlations of each NMME model are lower in JJA than SON, except for that CFSV2 model. But the root mean squared error never becomes saturated for any model in the early season. Now, negative RPSS values are present during JJA for models other than CFSV2, which is only very slightly positive, which indicates here that JJA forecasts are similar or worse than climatology when categorically forecasting for a distribution of below, near, or above normal ACE seasons. So finally, SON forecasts are faring much better in the deterministic skill metrics, especially those from the CMC2 CAN CM4, the CSM1, and the CCSM4 models. All these models have a positive, strongly positive RPSS value in SON as well. Excuse me, the most skilled being CCSM4. We also compute ROC curves associated with the respective JJA and SON forecasts for each of the below, near, and above normal ACE forecasts from each of the NMME model members. Just briefly, the ROC curve measures the forecast ability to differentiate between events and non-events. So a useful forecast would have high hit rates and low false alarm rates, such that the ROC curve would lie very close to like the top left corner. So an unskilled forecast would lie on or below the gray diagonal of the ROC curve, which would signify that false alarm rates occur as often or more often than hit rates do. And that would limit any potential effectiveness of the model. The points on each curve correspond to the number of ensemble members that are forecasting the event, and each NMME model is colored according to the legend here, right? So in JJA, the below normal forecasts outperform climatology, so they lie above this gray diagonal line. But they're not quite as skillful as the above normal forecasts. Only the CMC2 CAN CM4 model produces an improved forecast in the above normal case. Now during SON, the below normal ACE forecasts actually outperforms the above normal forecast for most of the NMME models. But both of these forecast categories are showing superior probabilistic forecast skill to that of climatology and to that of JJA. And this lower forecast skill in JJA may also be related in part to to a reduced Atlantic ACE signal in JJA, which could also be related to the decreased Nino 3 SST anomaly variance during JJA that the late season is seeing the benefit of. The near normal forecasts in the middle of both figures have little to no skall. So to summarize some of the predictability results, if we take this together with our previous understanding, these forecast skall metrics suggest that the Interbasin SST index has some utility in predicting both the below and above normal ACE seasons. So the greatest amount of skall is found in SON, which coincides with the growth of Nino 3 SST anomalies that are related to INSO's phase locking to the seasonal cycle and its peak in boreal early winter. The early season forecasts also improve on climatology, where the JJA above normal ACE forecasts have shown to have greater skall than in the below normal case. So these results are encouraging, especially as it appears that the high impact above normal ACE tercile is seeing increased predictability in both seasons. So to just sort of back up and summarize the main findings of this work, we're finding that the relative contribution of remote and local SST anomaly changes exhibit the relative contribution is exhibiting a seasonality, and so you see a change in the relative contribution of remote and local SST anomalies from the early to the late hurricane season. So there is the weak remote Nino 3 SST influence on Atlantic tropical cyclone activity during the during the early hurricane season, which is suggestive of an enhanced role of the remote of the local SST anomalies in the early season. However, we also see an enhanced role of the remote SST anomalies in the late season, and that is the relative weight of the local SST anomalies to that of the remote SST anomalies in the late season are fairly equal. We've built and tested an interbasin index that incorporates these remote and local SST anomalies and builds in that minimal early season Nino 3 impact on ACE, as well as that shared Nino 3 and NDR influence that occurs in the late season. This interbasin index, when coupled with NMME ensemble forecasts, it is able to make some skilled forecasts of above and below average ACE. And again, this is a very kind of promising result, because we're looking at some increased predictability of high impact tropical cyclone activity in both the early and late hurricane seasons. So finally, some topics for exploration here include a further investigation into the Interbasin SST relationship with some other relevant tropical cyclone fields. So it would be interesting to examine the role of the Interbasin SST relationship with specific environmental factors that modulate tropical cyclone activity in the Atlantic. So for example, the relationship with CAPE or vertical wind shear. It would also be useful to reevaluate this interbasin index forecast using a full suite of NMME ensembles that have been initialized from January throughout August. So it would be curious to see whether or not that probabilistic forecast skill would improve both in the early season or certainly during SON. And finally, an expansion of the Interbasin SST relationship to different modes and timescales of variability, such as the AMO or PDO, would help delineate whether the Interbasin SST index could actually be applied to represent something like multi-decadal hurricane variability. So with that, I'm finished, and I'll open up the floor for any discussion. So thank you.